Good morning, everyone. So our study focuses on modeling sediment transport from the Ganga Basin, located in the northern part of India, to the Ganga-Brahmaputra-Meghna Delta, or the GBM, southeast of the Ganga Basin. And a delta is just a landform created by deposition of sediment carried by a river to a slow-moving or a standing body of water. And if we look at the figure, the GBM delta is located roughly in that yellow square. So the GBM has a population of approximately 144 million people, and roughly 2/3 of the country of Bangladesh resides on that delta. In addition, the Sundarbans, a UNESCO World Heritage Site, and the largest Bengal tiger habitat reside on that delta. So not only is this a densely populated area, but it's also ecologically important. The GBM has a sediment deposition rate or aggradation rate of approximately 1 to 2 centimeters per year, all the while global mean sea level is rising at approximately 0.3 centimeters per year. Now, the middle and right figures display a bathtub model, and bathtubbing just shows how a landmass would be affected due to a certain amount of sea level rise. So if we look at the middle figure, the dark blue or the darker blue area in the red circle displays the landmass that would be affected with a 1 meter sea level rise. And similarly, on the right figure, the darker blue area in the red circle displays the flooding that would occur with a 1.5 or more meter sea level rise. However, these bathtub models are not accurate because they don't account for sediment deposition or aggradation of the delta. However, India is currently engaging in a water transfer project that may decrease that sediment deposition to the delta, so we may see some type of bathtubing effect occur in the delta. So what is this water transfer project? Well, it's called the National River Linking Project, or the NRLP, and when completed will connect 37 rivers and transfer approximately 174 billion cubic meters of water per year through a canal network of 14,900 kilometers. So this by no means is a small project and stands to be the largest water transfer project in the world. Now, the purpose of this NRLP is to increase hydropower in the country and reduce flooding in the east of the country. So this area right here, east, which is affected mostly by the monsoon season. But the main goal is to increase agricultural water resources in the south and west of the country, which are a lot drier. So the objectives for our study are to first quantify sediment transport to the delta, and then determine how the NRLP will affect sediment transport to the GBM. Now, these objectives are important because the NRLP will affect future water treaties between India and Bangladesh. If there is decreased sediment transport to the delta, there will also be decreased nutrient transport to Bangladesh's crops, which may have a significant economic impact. In addition, the NRLP will be undertaking some serious geomorphic engineering. So if there's populations that are living near rivers and those rivers are diverted, those populations will more than likely be displaced. And this, we can see this effect not only in India, but in Bangladesh as well. So to simulate sediment transport, we use a climate-driven hydrological and sediment transport model called Hydrogen version 3.0, and it was developed by Kettner and Silvestre. So we input basin properties such as precipitation, temperature, reservoirs, river networks, glacier characteristics, et cetera, and we run that through a water balance model to generate daily water discharge and sediment flux. Because of its size, the Ganga Basin is very heterogeneous in its characteristics. So here we have examples of lithology, precipitation, and temperature. And just by looking at these figures, we can see that there is variation across the Ganga Basin in characteristics. So we use those characteristics to break the Ganga Basin into 9 subcatchments, denoted by the top figure. We then simulate a mean annual discharge for each subcatchment. We add those discharges together, and then we compare the cumulative subcatchment discharge to our observed discharge at the Farakka barrage, denoted by that red star. So to observe some trends, we have discharge on the y-axis and time in months on the x-axis. And kind of right away, we see this huge peak represented by the green line for the months July through October. And we found that that actually correlates with the monsoon season. So it makes sense that we would see a peak that big during that time period. We first ran a simulation of the whole basin, so we didn't break it up, and we compared that to our observed data, and we noticed that there was a 47% difference in water discharge. And we determined that that could probably be in effect because of the monsoon season, and the model isn't distributing water to the model is not distributing water correctly during the monsoon season. However, when we broke up the Ganga Basin into our subcatchments, we noticed that there was only a 1% difference between our simulation and the observed data. So this suggests that by breaking up the basin into smaller subcatchments, the model becomes more accurate. Now, when we compare simulations that don't include our NRLP structures, such as proposed dams and river links, versus the simulations that do, we noticed that there was an 11% difference in water discharge. So just based on the water discharge validation, we noticed that during the drier months, based on our subcatchment delineation, the model underpredicts, and during the monsoon season, the water discharge is underpredicted. Now, we didn't have access to suspended sediment load validation data, so we used the sediment rating curve, which describes the relationship between water discharge and sediment load. We derived the equation from the Islam et al. 1999 paper. So S is suspended sediment load, Q is the water discharge, and the 0.007 and the 1.544 power were just constants that we derived from the equation. So again here, just to observe some trends, we have sediment load on the y-axis and time in months on the x-axis. So the orange line denotes our calculated suspended sediment using that sediment rating curve. And we see the same trend during the monsoon season, similar to the water discharge trend. The green line represents simulations that don't include the NRLP structures, and the purple line represents simulations that do include the NRLP structures. So when we ran the simulation of the basin and we compared it with our calculated suspended sediment load, we noticed that there was a 60% reduction. And again, that's attributed to the fact that the model is not feeding enough water during that monsoon season. So we see a huge difference. However, when we looked at simulations that compare the subcatchments without the structures versus with the structures, we noticed that there's only a 9% reduction in sediment. So again, suggesting that the NRLP structures will reduce sediment transport by 9% to the delta. So just to kind of revisit our bathtubing model, will we see effects such as this, such as the bathtub models occur? The answer is probably not. However, even though 9% sediment seems like a very small number, it may still have significant impacts to the countries of India and Bangladesh. So in India, what would happen is that sediment doesn't just disappear. It would more than likely be trapped upstream, clogging rivers. Downstream in Bangladesh, we may see effects such as decreased nutrient transport for croplands. So just some takeaways from our study. By breaking up the Ganga Basin into smaller subcatchments, our model becomes a lot more accurate. And then we also show that there may be a decrease in sediment transport by 9% just based on our subcatchment delineation. And again, based on our subcatchment delineation, we noticed that hydrotrend underpredicts water discharge during the monsoon season. So future work might look at using different subcatchment delineations to better the agreement between the observed between the observed data and simulated data as well. Our study also only looks at sediment transport from the Ganga River, so future work might include sediment transport from the Brahmaputra and Meghna rivers as well. And then we can also look to study the effects of the NRLP coupled with climate change scenarios. So I just want to thank my mentors, Stephanie Higgins, Keith Jennings, and Kimberly Rogers for their help with my research, UNAVCO and the RESESS program, which made this study possible, and NSF as well. Thank you, and I'm opening up the floor to any questions.
Any questions for Jose? Mike.
I have a question. So if the deposition rates are 1 to 2 centimeters per year, where's the accommodation space coming from to deposit all that sediment, for that sediment to stick around?
I'm sorry, can you repeat?
Where's the accommodation space coming from? Is there some subsidence of the landscape there to, right? Because you can't keep depositing sediment, otherwise you'd go above sea level. So what's allowing all that 1 to 2 centimeters per year to stick around?
You're right in the subsidence rates. So there's a study by Higgins et al. 2014 that looks at subsidence rates in the Bangladesh area, and there's certain areas that are subsiding at around 10 millimeters per year, where others, like outside the city, show smaller numbers or larger numbers. So there was some variation. So I don't think there was like an actual overall average that I found, but there is subsidence occurring in the delta that is allowing for that accumulation of sediment to not seem so, important in comparison to sea level rise.
And so, but if sea level rise is this fraction of a centimeter, whereas deposition rates are 1 to 2, it would seem, why wouldn't, with looking at 1 meter sea level rise and 1.5 meter sea level rise models, that wouldn't we see no actual, because if sea level goes up, you'd be depositing all that sediment, preserving it. So why would actually the sea seemingly transgress onto that landform instead of actually just staying where it is because of all the sediment deposition?
Okay, so those bathtubing models don't account for the sediment transport, the sediment delivery to the delta, but it does account for the subsidence rate. So as the delta is subsiding, the sea level is rising, so the sea level is going to encroach on the country.
Okay. Has someone then made the models? Does it seem like that would be a significant thing, that if they're depositing all that sediment, then why would they really be worried about sea level rise and the subsidence if that sediment is then filling in whatever space is being created with the subsidence and the increase in sea level?
There was a paper published by Darby et al. 2015 that looked at simulations that looked at sediment transport from the Ganga Basin, but it incorporated future climate change scenarios. And they did notice that there was an increase in sediment transport. So there kind of was a suggestion that there's no worry for sea level rise. But again, with the NRLP, we're not quite sure what the effects are going to be.
Thanks, Mike. I think we have an online question. Andrew, I think you can ask your question through your computer mic.
Oh, hi. Can you hear me?
Yes.
Hi, Jose. That was a really interesting presentation. I wonder if you've been able to share your results with Indian and Bangladeshi scientists, and if so, if there might be a chance for you to collaborate with them after the internship ends. Thank you.
So Andrew asked if Jose has had the chance to collaborate or share his results with Indian or Bangladeshi scientists, and if so, is there a chance for you to collaborate in the future after the internship?
So I haven't actually thought that far ahead. So my mentor is actually working on a broader aspect of this project that does include the Brahmaputra basin as well and the Meghna. So hopefully I'll be able to continue my work with my mentor, and we can publish our results, and there might be some effect in terms of, that aspect.
Thanks. Other questions? No? All right. Great job, Jose.
Thank you.